Okay, I just wanted to review a paper I just read that's cited by several other sources, The Evolution of Knowledge, Rethinking Science for the Anthropocene, so that's a book. So I'll leave that for now. Birth of Quantum Mechanics, and I'll leave that for now. And let's see what else we got here. And okay, leave that for now. And what else? Okay, so this one I didn't read yet. Right, so okay, I cite this in the video I made last night. And so here we have paper from 1977. Let's see what it says. One. Oh yeah, I already cited that too. Okay, so basically I did a new blog post on this. I'm going to go over that. And what was fascinating is basically this paper translation as heuristics, Heisenberg's turn to matrix mechanics. So Heisenberg realized he had to use an anharmonic oscillator from Fourier analysis, and then that was for the dynamics, but he was relying on spectroscopy data, empirical data, and he was trying to keep it as an empirical, positivist science, so based on the observation of the data. So he was focusing on the intensity of the transitional photons in the spectroscopy. But the classical Fourier analysis did not specify the intensity or the polarization of the emitted radiation. So he had to try to figure out how to develop a new mathematics to interpret the empirical data. And that's how quantum physics developed, and he never called it quantum mechanics. He just called it quantum kinematics, which would be his focus on the transitional amplitudes as the fundamental observations that are noncommutative. And so this is what Alain Kahn also explains, talking about the spectroscopy of the transitional frequencies. So the intensity in quantum physics is directly proportional to the frequency, which of course is from the photon-electron photoelectric effect that Einstein got the Nobel Prize for discovering based on Planck's constant. But what's fascinating is that Heisenberg had to turn from the calculus differential into a classical difference equation. And this, of course, brings me back to music theory, because obviously the non-Western Pythagorean music theory is based on discrete numbers as difference. And So like I said, Heisenberg had to use an anharmonic oscillator to apply these difference equations as dynamics. And the crucial point was that the multiples of the fundamental frequency, the overtones, as transition frequencies were not multiples of the fundamental frequency. And that's why you couldn't use complex Fourier analysis. And so the sums of the transitions frequencies end up being non-commutative. So when you square the frequencies, it was ended up being different from the classical Fourier analysis. So then Heisenberg invoked the combination principle from the Ritz-Rydberg combination principle, so that each radiation frequency as a discrete frequency could be written as a difference of the two terms. And this again is precisely what you do in music theory. You have the octave and the root tonic, and the perfect fifth would then be non-commutative. The frequency of a radiative transition was equal to the sum of the frequencies occurring in a two-step transition via an intermediate state. So this is exactly what this is the core concept of the non-commutativity. And so the key point here is when they got turned into matrices, then it was the total transitions as a non-locality, and that's why Heisenberg never relied on the totality of transitions, because he was still connected to the actual empirical data of the spectroscopy. So when you use the matrices, you get an infinite series for each individual overtone. Well, this is what Heisenberg was working on when you go to the second derivative based as the dynamics. And using just the classical complex Fourier series, it would be trivial, but he was using a real number Fourier series, so he could split it into two distinct ways, meaning it's non-commutative. And so this is where he describes it as the order of the overtones. So that's precisely the same thing you find in music theory, is the transitional frequency is actually the order of the overtones. In this case, again, the perfect fifth would be non-commutative based on the order of the time in relation to the frequency. So that's why he had to use discrete differences and not classical or differentials. And so here you have to multiply the negative frequencies to then convert it to amplitude for the energy of the observable. And so when you multiply the negative frequency, that's where you cancel out the non-commutativity. And because of that multiplying process, Heisenberg then started to move away from the real number Fourier analysis. So then when it was translated into matrix mechanics, that became the probability amplitude as all possible transitions. And so, but when you have the non-commutativity, the problem is you lose the conservation of energy, because you have this order of the overtone being non-local, so the conservation of momentum directly proportional to frequency is no longer maintained as symmetry, so it's no longer conservation. And that applies directly to the quantum biology that Pascual Jordan was arguing it's the secret of the noncommutativity. So this whole process that Heisenberg went through, it invalidates the notion that noncommutativity was his seminal insight. So for Heisenberg, it was still a problem, and that's why he was writing to Wolfgang Pauli about this, and Wolfgang Pauli was like, no, you got to get rid of the noncommutativity. And so for Heisenberg, the noncommutativity was still unresolved. So that's why they came up with the matrices. Like they realized that that's in the matrix mathematics, and then using the matrices, they could get rid of the noncommutativity as the identity matrix. And so in my video last night, I explained why that's problematic, because you're trying to claim that the imaginary number is not, when you have negative I, you can just cancel it out by squaring it, but that cancels out this order of the overtones as the discrete negative frequency. So that's where the term quantum mechanics was established, but Basil J. Hiley is saying it's not mechanics, because you have this deeper algebraic process that's discrete and non-local and non-commutative. So Heisenberg was trying to rely on the directly observable quantities, and therefore emphasizing the transitional amplitude after you square the discrete numbers. And then when it got into matrices, it became a dynamics, but they still had a problem because the time derivative of the position matrix did not coincide with the momentum matrix of the time derivative. So that's why you have this Heisenberg uncertainty principle was actually a product of the matrices that was developed, but it originated from this deeper time frequency uncertainty, or actually the non-commutativity. So then Dirac later realized that if you use the Poisson brackets, you can translate this difference of the time derivative into partial differentiation. And so that's what Basil J. Hiley was critiquing, was that you have this Jordan bracket that actually got covered up and ignored when the commutators were developed for the matrix mathematics. So that's pretty much it. And that's why you have this intrinsic weirdness, because ever since people have been confused about what is the true meaning of quantum mechanics. And they're pointing out that this is a similar role that the Archimedean point has for the equivalence principle for Einstein's relativity. And so Roger Penrose, he points out that actually the uncertainty principle is more fundamental than the equivalence principle in relativity. So now we look at who cites this paper. I was looking at the Pascual Jordan, what's the update? Let's see what they say about this non-commutative. Non-commutativity acquires an intuitive meaning that directly expresses what is contained in complementarity. Okay, so again, it's all based on the observables, but when you're relying on listening as meditation, then you can bypass that paradox of the observables. Okay, so as I mentioned last night, the spin then corroborated Pascual's Jordan claim that it's inherently non-commutative. So the spin is neither a wave nor a particle.